Yesterday, at approximately 0300 hours Coordinated Universal Time, something extraordinary happened in the geometry of space between Earth and 3I Atlas. The interstellar comet reached what astronomers call perfect opposition, an alignment so precise that the Sun, Earth, and comet formed nearly a straight line with a phase angle of just 0.69 degrees. To put this in perspective, this is one of the smallest phase angles ever observed for such an object, and it creates a viewing geometry we rarely get to witness. The comet appeared fully illuminated from our vantage point, exactly like a full moon in Earth's night sky, with sunlight hitting it directly from behind us and eliminating almost all shadows across its visible disk. This is not just a beautiful cosmic coincidence. Let's look closer at the data, because this alignment triggers a phenomenon that could dramatically change what we see. When a solar system body reaches this kind of opposition geometry, it can experience what's called an opposition surge, a sudden spike in brightness that can increase by several tenths of a magnitude over just a few days. The effect comes from two related processes happening simultaneously in the dust and regolith covering the comet's surface. The first process is shadow hiding. Imagine standing on the comet's surface looking back toward Earth and the Sun directly behind it. Every particle of dust, every grain of ice-covered rock casts a shadow away from the Sun. But when the Sun is directly behind the observer, those shadows fall directly behind the particles themselves, hidden from view. The particles mutually obscure their own shadows. The second process is more subtle and depends heavily on the physical properties of the dust itself. It's called coherent backscattering, where light waves bouncing off multiple particles interfere constructively when they return along nearly the same path they arrived, creating an additional boost in brightness. Here is the crucial detail. The strength of this opposition surge depends entirely on what 3I Atlas is actually made of. If the surface dust is primarily carbonaceous material with a low albedo around 0.03, the surge will be more subdued. If there are significant amounts of icy grains with higher reflectivity, or if the dust is arranged in porous fractal aggregates rather than compact particles, the effect could be much more pronounced. The packing density of the surface layer matters enormously. This is why the next few days of observations are absolutely critical. As of today, January 23rd, we are inside the peak window for this opposition surge. Observatories around the world and in orbit are collecting photometric data to measure any brightness increase and, more importantly, to characterize exactly how the light is being reflected. If you've been following this story and want real-time updates as the data comes in, this would be a great time to subscribe, because the results from this opposition window could fundamentally change our understanding of what 3I Atlas is made of and where it came from. But there's another element to this perfect alignment that makes it even more significant. The anti-tail, that unusual sunward-pointing structure stretching over 400,000 kilometers back toward the Sun, is now aimed almost directly at Earth. From our perspective, we're looking straight down the barrel of this structure. The tiny phase angle means we're seeing it edge-on with optimal illumination. This gives us the best possible viewing geometry to study the unusual dust grains responsible for the anti-tail's persistence and the polarization anomalies that have puzzled researchers since early observations. The comet is also releasing volatiles, water vapor, carbon dioxide, trace amounts of cyanide compounds, all dispersing harmlessly into space due to the comet's high velocity of tens of kilometers per second and the pressure of the solar wind pushing material away from the inner solar system. But with the current alignment, spectrographs can measure these emissions with unprecedented precision, looking through the least amount of intervening material. So what does this actually mean for the bigger questions surrounding 3I Atlas? The opposition surge data will tell us about surface composition and particle structure. The anti-tail observations will help resolve whether those larger-than-average dust grains are simply a natural result of the comet's formation environment or whether something more unusual is at play. And the volatile measurements will give us chemical signatures that might point toward the interstellar cloud where this object originated. We are in the peak data collection window right now, and what we learn in the next 72 hours could either put some of the mysteries to rest or deepen them significantly. While the opposition event captures immediate attention, newly processed imagery from the Hubble Space Telescope has just revealed something that changes the entire conversation about 3I Atlas. The images come from an extensive observation campaign, 24 separate exposures spanning late November 2025 through mid-January 2026, and the processing technique used is as important as what it revealed. The challenge with photographing an active comet is that the coma, that glowing cloud of gas and dust surrounding the nucleus, overwhelms any surface features or smaller structures. Traditional image processing can subtract the coma to some degree, but Hubble's team used something more sophisticated, rotational gradient filters that track the comet's rotation and strip away the diffuse coma while preserving rotating structures tied to the nucleus itself. Think of it as watching a spinning lighthouse through fog and using the rhythm of the rotation to filter out the fog and see only the beam. What emerged from this processing is astounding. 3 distinct mini-jets, each extending outward from the nuclear region to approximately 25,000 kilometers, positioned at exactly 120 degrees apart from each other. Picture an equilateral triangle or a 3-bladed propeller. This is not approximate. The angular spacing is precise to within measurement error. The jets form a stable tripod configuration that has persisted throughout the entire observation period. Let's look closer at the data because the geometry gets even more remarkable. These mini-jets are not static. They oscillate coherently, swinging back and forth plus or minus 20 degrees from their central positions over a precise period of 7.1 hours. This period matches the comet's rotation or tumbling period with extraordinary accuracy. The motion is synchronized. All 3 jets move in concert, maintaining their 120-degree spacing throughout the oscillation cycle. The spin axis of the comet appears to be tilted only 10 to 20 degrees from the Sun-comet line. This means that from the Sun's perspective, or from Earth's perspective during opposition, the comet appears nearly pole-on, and the rotating tripod of jets creates the appearance of a rotating beacon. The ordered geometry is undeniable. The dominant anti-tail extends much farther, but these 3 mini-jets represent something different, a highly symmetric structure emanating from the nucleus itself. This contradicts what we previously thought about how cometary jets form. Natural jets are caused by sublimation of volatile ices, water, carbon monoxide, carbon dioxide, exposed on the surface or just beneath it. As sunlight heats the nucleus, the gas erupts outward, carrying dust particles with it. But natural sublimation-driven jets are typically chaotic. They're controlled by where patches of ice happen to be exposed by topography, by the random history of impacts and fractures on the comet's surface. You might get 2 jets or 4 or a dozen, but they're rarely symmetric and they're almost never equally spaced around the rotation axis. 120 degrees is special in engineering. It's the minimal stable configuration for 3-dimensional attitude control. Spacecraft often use 3 reaction wheels or 3 thrusters spaced at 120 degrees to efficiently control orientation in all 3 axes. It's the geometry you choose when you want stability and efficiency. Seeing this same configuration on a natural object raises immediate questions. Could this be natural? Absolutely. If the nucleus formed with a particular crystalline structure, or if impacts early in its history created fracture patterns that happen to have 3-fold symmetry, or if there's some kind of resonance between the rotation and internal heat distribution that focuses sublimation at 3 specific longitudes, then nature could produce this geometry. Prolonged processing by cosmic rays during millions or billions of years in interstellar space could create unusually durable dust structures with specific properties, but the precision is what keeps researchers awake at night. The 7.1-hour oscillation period is exact. The 120 degrees spacing is exact. The coherent motion is exact. The stability over weeks of observation is exact. Each of these individually might be explained by natural processes, but all of them together in one object creates a pattern that stands out statistically. Avi Loeb and Marco Barbieri both emphasized the significance of this geometry in statements released on January 21st, the day before the opposition event. They stopped short of drawing conclusions but made it clear that the Hubble imagery adds a new dimension to the analysis. The three-jet configuration is now the centerpiece of discussions about what 3I Atlas actually is and whether all of its features can be explained by conventional cometary physics alone. Now, with the comet at perfect opposition, the anti-tail structure stretching over 400,000 kilometers back toward the Sun is aimed directly at Earth, giving us an unprecedented opportunity to understand one of 3I Atlas's most persistent anomalies. Anti-tails are not unheard of in cometary science. Their projection effects, visible when Earth crosses the orbital plane of a comet and we see the dust tail from an edge-on perspective. But what makes 3I Atlas's anti-tail unusual is its composition and behavior. The dust grains forming this anti-tail are significantly larger than average for cometary dust. Typical cometary dust particles range from submicron to a few microns in size, small enough to be pushed away from the Sun by radiation pressure, creating the classic dust tail that always points away from the Sun. But larger grains, tens to hundreds of microns in diameter, are too massive for radiation pressure to move them efficiently. They lag behind the comet in its orbit, spreading out along the orbital path. When viewed from the right geometry, this lagging dust creates the illusion of a tail pointing toward the Sun. Let's look closer at the data from polarimetry studies. Light reflecting off dust particles becomes partially polarized, and the degree and direction of polarization depends on the particle size, shape, composition, and how they're aggregated. 3I Atlas's anti-tail produces polarization signatures that don't match standard models for cometary dust. The polarization angle and the way it changes with phase angle suggests either unusually compact grains, a different composition ratio between silicates and carbonaceous material, or aggregate structures with specific fractal dimensions. Here is the crucial detail. During opposition, with the phase angle at just 0.69 degram, polarimetry reaches a unique measurement regime. At very small phase angles, the polarization can actually reverse direction, a phenomenon called negative polarization branch. The exact phase angle where this reversal happens and how deep the negative polarization goes depends intimately on the surface texture and composition of the dust grains. The measurements being taken right now during this narrow opposition window will constrain these properties with precision we cannot achieve at any other geometry. Amateur observers and professional facilities captured images on the evening of January 22nd showing the anti-tail's forward appearance, dramatically emphasized by the tiny phase angle. From Earth's perspective, the anti-tail appears to point almost directly toward us, foreshortened by the viewing angle but intensely illuminated. The Virtual Telescope Project conducted a live observation session timed precisely to the opposition moment, capturing the comet in what they described as its full moon phase configuration. Raw data processing continues, but preliminary images already confirm the predicted geometry. So what does this actually mean for understanding the anti-tail's origin? If the dust grains are simply larger than average due to the comet's formation environment, perhaps originating in a denser region of its parent molecular cloud where grain growth was more efficient, then the polarization data will match models for large but otherwise normal silicate and carbon-rich particles. If something about the comet's long journey through interstellar space altered the dust properties, cosmic ray bombardment over millions of years, creating unusually radiation-damaged or polymerized organics, the polarization signature would show specific anomalies. The volatile releases add another layer to the mystery. Water vapor, carbon dioxide, and trace cyanide compounds are escaping from the nucleus and dispersing into space. The high velocity of the comet, tens of kilometers per second relative to the Sun, combined with the outward pressure of the solar wind, ensures these volatiles disperse harmlessly and pose no threat to Earth or any other body in the solar system. But the chemistry of these volatiles carries information about the comet's origin environment. Cyanide compounds in particular are interesting. They form readily in cold molecular clouds and are common in comets. But the ratios between different cyanide species, hydrogen cyanide versus methyl cyanide versus cyanoacetylene, depend on the temperature and density conditions during formation. Spectrographic measurements during the opposition window, looking through the anti-tail with minimal intervening coma, provide the cleanest possible measurements of these ratios. What questions should we be asking about this data? Do the dust properties suggest a formation environment different from solar system comets? Does the chemical signature point toward a specific type of interstellar cloud or a specific region of the galaxy? Are there any trace elements or isotopic ratios that look anomalous? If you have thoughts on what the anti-tail observations might reveal or what additional measurements would help resolve these questions, the comment section would be a great place to share them. This is exactly the kind of data-driven mystery where fresh perspectives can suggest new analysis approaches. The anti-tail will remain visible for several more weeks as the comet recedes from the inner solar system, but the opposition geometry is already past its optimal window. The measurements taken yesterday and today represent the peak opportunity. Results will begin appearing in preprint archives within days as research teams complete their initial analysis. Avi Loeb has compiled a list of 18 documented anomalies associated with 3I Atlas, and he's placed the object at level 4 on his techno-signature scale. To understand what this means, we need to be clear about what the scale represents and what it doesn't. It's not a declaration that 3I Atlas is artificial. It's a framework for quantifying how many standard deviations an object's properties deviate from what we expect for natural bodies. Level 4 means the combination of anomalies is statistically unusual enough to warrant serious investigation, but it does not mean natural explanations are exhausted. The 18 anomalies span multiple categories. The polarization irregularities we've discussed are several items on the list. The precise 120-degree spacing of the mini-jets is another. The 7.1-hour oscillation period with its coherent motion across all three jets. The anti-tail's unusually large dust grains. The stability of all these features over weeks of observation. The spin-axis alignment producing the beacon-like appearance. Each individual anomaly might have a natural explanation, but the combined probability of all 18 occurring simultaneously in one object becomes progressively smaller. Let's look closer at the data comparing 3I Atlas to spacecraft systems. A three-jet configuration spaced at 120 degrees is exactly what you'd see in a minimal three-dimensional attitude control system. Spacecraft use this geometry because it's mathematically optimal. Three control actuators, whether they're reaction wheels, thrusters, or magnetic torquers, placed at 120 degrees around a central axis, can generate torques in any direction with minimal redundancy. It's elegant engineering. The oscillation pattern is equally suggestive. If those jets were producing small amounts of thrust, not enough to significantly alter the comet's trajectory, but enough to control orientation, you'd expect to see periodic motion as the jets fire in sequence, or as the spacecraft rotates through its control cycle. The 7.1-hour period could be a natural rotation period, or it could be a control system maintaining a specific orientation with periodic corrections. This is where the conversation becomes difficult because we're pattern matching against human engineering. The danger is obvious. We evolved in an environment where recognizing patterns was survival critical, and our brains are exceptionally good at seeing patterns even in random noise, faces in clouds, messages in static, order in chaos. This is why the scientific method demands extraordinary evidence for extraordinary claims, and why researchers like Loeb are careful to present these observations as questions rather than conclusions. So, what are the natural explanations still on the table? Prolonged cosmic ray processing is one of the most promising. 3i Atlas has potentially been traveling through interstellar space for millions or billions of years, exposed to galactic cosmic rays without the shielding protection of a stellar wind. This prolonged bombardment could alter the molecular structure of surface materials, creating unusually durable organic polymers or radiation-damaged silicates with specific optical properties. The larger dust grains could be a direct result of this processing, with smaller grains eroded away or aggregated into larger structures over time. The three-jet geometry could emerge from internal structure. If the nucleus has a crystalline lattice with threefold symmetry, perhaps formed during its original accretion in a molecular cloud, then sublimation might preferentially occur along crystal boundaries or defect lines that happen to align at 120 degrees. It would be unusual, but not impossible. This contradicts what we previously thought was required for technosignature detection. The assumption has always been that artificial objects would show clear signs of fabrication, geometric precision, far beyond what natural processes can achieve. Materials with properties impossible to create without industrial chemistry or active propulsion systems changing trajectories in ways that violate orbital mechanics. 3i Atlas doesn't clearly show any of these. Its trajectory is consistent with a hyperbolic orbit shaped only by gravity. Its composition, as far as we can measure, consists of materials found in natural comets. But what if artificial doesn't mean large spacecraft? Speculation, and it's important to emphasize this is speculation, includes the possibility of embedded mini-probes, small devices incorporated into an otherwise natural body capable of making small course corrections or collecting data while remaining largely undetectable. Could a civilization seed interstellar space with instrumented comets using natural bodies as carriers? Could 3i Atlas be a marker or beacon like ancient pyramids announcing the presence of intelligence to anyone capable of detecting the anomalous patterns? The counter-argument is straightforward. Why would an advanced civilization use such ambiguous signals? If you want to be detected, why not use clear, unambiguous markers? If you don't want to be detected, why include any anomalies at all? The apparent middle ground, detectable but only with careful analysis, seems either accidentally incompetent or deliberately cryptic, and neither makes obvious sense as a strategy. Here is the crucial detail that keeps this discussion scientific rather than speculative fiction. Every single anomaly must be quantified, measured, and compared against models. The 18 anomalies on Loeb's list are not subjective impressions. They're measurable deviations from expected values. The next phase of analysis involves building detailed models of natural formation and evolution processes to see if the combination of anomalies can be reproduced without invoking artificial origins. If natural models can account for all 18, the technosignature hypothesis loses support. If some anomalies remain unexplained, even by the most generous natural models, the investigation intensifies. The Virtual Telescope Project's live observation on the evening of January 22 successfully captured 3i Atlas at the precise moment of opposition. And while detailed data processing continues, the initial results confirm the geometric predictions. The comet appeared as anticipated, fully illuminated with the anti-tail prominently displayed pointing forward from Earth's perspective. The opposition surge measurements are ongoing, with photometric data being collected by multiple facilities to characterize any brightness increase over the next several days. As of today, January 23, the comet is fading from its peak apparent brightness, now dimming toward magnitude 13 as it recedes from both Earth and the Sun. It's currently moving beyond the orbit of Mars, heading back toward interstellar space on its hyperbolic trajectory. There is no threat to Earth, Mars, or any other solar system body. The trajectory is purely gravitational, and the comet will exit the solar system completely within the next year, likely fading beyond detection range for all but the largest telescopes within months. So what does this actually mean for resolving the mysteries? The data collected during the opposition window represents the peak observational opportunity we're going to get. The polarimetry measurements at 0.69° phase angle are now complete, and analysis teams are comparing the results against models for different dust compositions and structures. These results will begin appearing in preprint archives within the next week to 10 days, and they'll either constrain the dust properties tightly enough to match known natural materials, or they'll reveal additional anomalies that don't fit existing models. The opposition surge measurements will take slightly longer to analyze because they require comparing brightness measurements taken over several days to isolate the surge component from the comet's intrinsic brightness and any activity changes. But preliminary indications should be available within 2 weeks. A strong opposition surge would suggest a surface rich in high-albedo icy materials with a loosely packed structure. A weak or absent surge would point toward low-albedo carbonaceous materials with a more compact arrangement. The Hubble imagery of the 3 mini-jets has already been processed, but deeper analysis continues. Research teams are building 3-dimensional models of the jet structures, tracking their motion through the full rotation period, and attempting to identify any asymmetries or irregularities that might point toward natural formation mechanisms. If the jets show any wobble, any deviation from perfect 120-degree spacing, any change in their oscillation pattern over time, those details would strengthen natural explanations. If they remain perfectly symmetric and stable, that strengthens the case for further investigation. Spectroscopic data on volatile releases will provide chemical and isotopic ratios that can be compared against solar system comets and interstellar molecular cloud models. Deuterium to hydrogen ratios, carbon isotope ratios, nitrogen isotope ratios, and the relative abundances of different cyanide species all carry information about formation temperature and density. Results should appear within a month as spectrographs complete their data reduction and calibration. Let's look closer at the data timeline. Peak polarimetry results arrive first within days. Opposition surge analysis follows in 2 weeks. Detailed jet modeling and spectroscopy results appear over the following month. By late February or early March 2026, we should have a comprehensive picture from the opposition window observations. This data will either converge toward a coherent, natural explanation or reveal deeper puzzles. Here is the crucial detail about what comes after the opposition data. As the comet fades and recedes, opportunities for detailed observations diminish rapidly. By April, it will likely be too faint for spectroscopy except with the largest telescopes under ideal conditions. By summer, it may be beyond practical detection range entirely. This makes the current data collection period absolutely critical. What we learn now is likely all we're going to learn about 3I Atlas unless someone proposes a space mission to intercept it. And given its high velocity and hyperbolic trajectory, that would be extraordinarily challenging, even with dedicated propulsion technology. Could future missions reach it? Theoretically, yes. But the delta-v requirements would be enormous. The comet is traveling at tens of kilometers per second relative to the Sun, and matching that velocity would require either a very long flight time with gravitational assists or a very large and expensive propulsion system. The European Space Agency's Comet Interceptor mission is designed for opportunities like this, but it hasn't launched yet, and 3I Atlas is probably moving too fast to be a viable target even when it does. This contradicts what we previously thought about interstellar object observation strategies. The assumption was that we'd have multiple opportunities as more interstellar visitors were discovered, each one providing additional data points. But 3I Atlas's combination of anomalies may be unique. If the next interstellar object behaves like a perfectly normal comet or asteroid, that would actually make 3I Atlas more significant by contrast, suggesting it's an outlier rather than representative of interstellar populations. The story of 3I Atlas is far from over, even as the comet itself fades into the darkness beyond Mars. The data collected during these critical weeks in January 2026 will be analyzed and debated for months or years. The object has already secured its place as one of the most intriguing interstellar visitors ever detected. And regardless of whether the final explanation is purely natural or hints at something more, it's expanded our understanding of what's possible in the galaxy around us.